This is lesson 4 in the transition metals unit from F325. This lesson covers stereoisomerism found in complex ions. If you remember back to AS chemistry, we covered one type of stereoisomerism, which was EZ isomerism, and a specific type of EZ isomerism, which was cis-trans. The learning objectives for this lesson are to describe stereoisomerism in transition metal complexes, giving examples of cis-trans and optical isomers, and to be able to draw cis-trans and optical isomers of familiar and, importantly, unfamiliar transition metal complexes. This is a common exam question, so you'll need a pen and plenty of paper in this lesson to practice drawing the different types of isomers. To begin, as always, with some definitions. The definitions of stereoisomerism is when a species has the same structural formula but different arrangement of atoms in space. Sorry. There are two types of stereoisomerism in transition metal chemistry. These are cis-trans and optical isomers. Cis-trans isomerism arises due to restricted rotation in the transition metal complex and can occur with monodentate, bidentate ligands or a combination of the two. Optical isomers are non-superimposable mirror images, and you came across these in F324. In transition metal chemistry, optical isomers can arise in octahedral complexes with coordination number 6. Now to work through some examples. Let's start with the easiest one. This is a square planar complex with coordination number 4. In order for there to be cis-trans isomerism, there needs to be two different ligands, two of each. So for example, NiCl2, NH32. Cis isomers are formed when the same ligand is on the same side, and trans isomers arise when the same ligand is on different sides. This is shown on the diagram in the slide. On the left-hand side, we have the cis isomer with the two chloride ions coming out, pointing at you, and the two ammonia ligands going back behind the screen. For the trans isomer on the right-hand side, we have one of each isomer coming out at the front, and one of each ligand coming out at the front, and one of each ligand going behind the screen. Remember, the wedges mean that the bonds are coming out in front of the screen, and the dashed lines mean the bonds are going back. Have a go at drawing the cis and trans forms of the complex ion platin, which has the formula PtCl2NH32. The structures are on the next slide, so you may wish to pause the video now. Now let's move on to cis-trans isomerism in complexes with the coordination number 6 with an octahedral shape. If the complex contains 6 monodentate ligands, 4 of one ligand and 2 of another, then it can exist as cis and trans isomers. To determine whether or not the ion is cis or trans, you need to locate the ligand that there are only 2 of. If both of these ligands are at 90 degrees to each other, the isomer is cis. If both of these ligands are at 180 degrees to each other, then the isomer is a trans isomer. This is best shown in the diagram. This is a cobalt complex ion which has different colours depending on whether it is cis or trans. CO, NH34, Cl2, with an overall charge of +1, contains 4 ammonia ligands and 2 chloride ions. If the 2 chloride ions are at adjacent corners to each other and at 90 degrees to each other, it is cis, as shown in the diagram on the left. If they are at 180 degrees and opposite to each other, then it is a trans isomer, as shown on the diagram on the right. Again, notice that these are drawn with wedged and dashed bonds, so that the bonds are coming out of the screen or back behind the screen. Octahedral complexes containing 2 bidentate ligands and 2 monodentate ligands can also show cis-trans isomerism due to restricted rotation. The slide shows the cis and trans isomers of Cr, C2O42, H2O2 with an overall charge of -1. In the bidentate ether dioate ion, C2O42-, each oxygen donates a pair of electrons to form a coordinate bond with the chromium, and there are 2 water monodentate ligands. Remember to show the bond with going to the oxygen, as the oxygen is the species that donates the electrons for the bond. Again, you need to identify the monodentate ligand that there are 2 of. And if these are at 90 degrees, it is cis isomer, as the one on the left is, and if they're at 180 degrees, then it is a trans isomer, shown on the one on the right. So, now moving on to optical isomers. To recap, optical isomers are non-superimposable mirror images of each other. Optical isomers can exist with A, a complex with 3 bidentate ligands, B, a complex with 2 bidentate ligands and 2 monodentate ligands, and C, a complex with 1 hexadentate ligand. The example given in the syllabus is Ni, NH2, CH2, CH2, NH2, 3, with an overall charge of +2, and this is shown on the next slide. This has a coordination number of 6 and is composed of a central transition metal ion with 3 bidentate ligands, ethane 1,2-diamine. When drawing these isomers, you just need to draw one isomer, draw in the mirror line, and then draw the mirror image of it. Now it's your turn to have a go at drawing the optical isomers for a complex. This complex is CO-En2Cl2. Remember that ethane 1,2-diamine is often shortened to En. Pause the video here, as the next slide will give you the answer. It doesn't matter exactly where you've put the ligand, as long as what you've drawn is the correct structure and the 2 isomers are mirror images of each other. A common exam question involves complexes that show both types of isomerism, cis-trans and optical. Complexes with 2 bidentate and 2 monodentate ligands show both of these types. And you may be asked a long answer question where you have to define both types of isomerism and use an example to illustrate them. You can have a go now if you wish with the complex Cr C2042 H2O2 with an overall charge of -1. We came across this earlier in the lesson. This may help to aid your understanding. If we go back to our learning objectives for this lesson, you need to be able to describe stereoisomerism in transition metal complexes by giving examples of cis-trans and optical isomerism, and draw cis-trans and optical isomers of familiar and unfamiliar complexes. During class time, you will need to be able to define the key terms we've used in this presentation and draw unfamiliar structures of different isomers. I'll see you then.